Welcome to the afternoon session of solid superacids. Those of you who don't know me, I'm Scott Hahn. I'm pinch hitting, to use a baseball term, for John Anderson, who unfortunately could not be here today. I have a couple of quick administrative things. Some people have inquired about these proceedings that we're planning on. Unfortunately, because of the situation with the two other organizers and some hectic situations at Mobile, which you probably have heard about, looks like the time will not be there to carry this out. In its place, we'll probably send something into applied catalysis, going on about the meeting and all that. But we will unfortunately not be able to pull together proceedings in a timely fashion, which I think is needed. With regard to the poster session, again, it's from 5 to 7. Please have your posters up if you by about a half hour before then. I invite everyone, please come to reception. We have very nice hors d'oeuvres, courtesy of Magnesium Electron. They want to support it, and it's just a shame that Peter Moles couldn't be here to accept the accolades from us for that. Okay, I take great pleasure in announcing introducing our second keynote speaker. Those of you who've dabbled in the area of solids, acids, and bases know about Professor Tanabe's accomplishments. And he is going to review in the solid superacids area for us today. And the title of his talk is Solid Superacids of Sulfated Metal Oxide Type.
Thank you, Chairman. We are a pleasure to have this opportunity to review about sulfated metal oxide type superacid. Now, the content of my talk this afternoon is the kinds of solid superacids, reaction catalyzed by solid superacids, and the property, the structure, preparation method, and comparison with other strong acids, and finally future trend of solid superacid. But time for presentation is limited. I will talk mainly about the kinds and reactions and comparison and the future trend of SSA. And the property, the characterization, preparation method were already presented this morning. So mainly reactions. What kinds of reactions are catalyzed by solid superacids? Now, I just summarize the solid superacids. So many kinds of superacids have been developed. This is homogeneous, this is heterogeneous. So sulfated metal oxide, this is the year of first publication. So sulfated zirconia silica was first published in 1991. So all one is SO4 2 minus. Supported zirconia 1980 was reported by Professor Arata. Now we have many kinds of solid superacids and homogeneous superacids supported on metals, and silica alumina itself shows superacidity, and heteropoly acid and Nafion H. Today Professor Ola presented about the activity of Nafion H. And now acid strength, here is H0 function. Well, it's different for the same catalyst here, 94. Someone said minus 13, someone says minus 16. And also this one, sulfated alumina, were different acid strengths. This is probably due to the preparation method and the measurement method of solid superacid. And you can notice where alumina itself shows superacidity. This was the superacidity was measured in the vacuum system. So correct measurement was carried out, and it showed superacid alumina itself. So we have now many kinds of solid superacid, and at present, superacid, the word, is no more surprising. Many kinds, even silica zirconia, silica titania, or titania zirconia, then just mixed oxide, is kind of solid superacids. Now, recently, higher acid strength were found. Now, this is Professor Ora said magic acid from stronger than this line, but the magic acid. So candlewood is easily melted in this solution. So he named magic acid. Now, as heterogeneous superacids were iron, mangan, sulfate, modified zirconia, 92, and phosphoric acid, BF3, and sulfuric acid supported silica with all very strong solid acid. It was reported 1988. Probably more, stronger acid may be found in near future. Now, then we see what kind of reaction are catalyzed by solid superacid. Isomerization by alkanes, and alkylation, halogenation, and oligomerization, cracking, combustion, and acylation. These reactions require superacid or strong acids. So it is a very important reaction. I talk about some details of these reactions later. And the second group of the reactions, these were esterification, dehydration, dealkylation, oligomerization, ring opening polymerization of THF, isomerization on butene, olefin, MTB synthesis, disproportionation, reduction of nitrogen oxide with ammonia, and partial oxidation of propane. Now, these reactions do not necessarily require superacid, while much weaker acidic catalysts catalyze these reactions. Nevertheless, even for these reactions, solid superacids shows very pronounced catalytic activity and selectivity, in some cases, a long life. I'll talk about these reactions. Now, so I'll show you several examples of the reaction, first group of reaction. Well, this was reported about 10 years ago by Cosmo Petrochemical Company in Japan. This is pentane, isopentane, and sulfated zirconia is sharply deactivated. So they put platinum on sulfated zirconia, and hydrogen, where it flowed in reaction reaction mixture. In that case, activity and selectivity were it's constant. And present catalyst life is 6 months. Well, last August, I'm told Cosmo Corporation in cooperation with an American company, will develop this process next year. If it is materialized, this is the first example of industrial application, but not yet. This type of isomerization is very important to get high octane value gasoline. However, by isomerization, isomerized, skeletally isomerized products has relatively low octane value. That's the problem. So it's not so ideal process. Nevertheless, it is going to be developed in industrial process very soon. Another topic is modified sulfated zirconia. As you know, this morning, this type of solid superacids were discussed. It's 1,000 times higher than that of sulfated zirconia. And this catalyst was discovered by Dr. Su of Sun Refinery and Market Company. And he says, this is the fluorobenzene and difluorobenzene and benzene. Now just you see the difference between these solid superacids. Apparently, acid strength is higher in this case, and also the acid amount is also larger. So this is one of the progress of sulfated zirconia type solid superacids. Now, second one is this one. Well, this is a very important reaction, alkylation reaction. Many people attempted to carry out this type of reaction because the products by alkylation has a high octane value. However, catalyst deactivation is very severe. So this is not promising for industrial application. Nevertheless, Colma recently reported sulfated zirconia shows very high selectivity for this compound and higher than zeolite B. But catalyst life is shown that vitally were defective point. And another important reactions is a methane with ethylene. This was reported was many years ago. Skure, South Africa, reported sulfated zirconia, C3 to C5 hydrocarbon obtained by using solid superacid. It's very important. This is utilization of methane to useful chemicals. This is a very impressive result to me. And last year, Professor Blender reported solid superacids. This is sulfated zirconia plus platinum. Is very active for dyschlorine with N-heptane. He carried out many kinds of reactions like this, and selectivity is well. Now, this one is superacid is also active for this kind of reaction. Another one, utilization of methane, is a chlorination of methane to give methyl chloride. Now, sulfated zirconia and iron mangan promoted one is also shows very high activity. No, this one is very high activity, and this is the ratio, and also this is selectivity 5. In this case, the lower activity but high selectivity. And this morning, George Ola talked about this reaction by using Nafion H. He says it's a good catalyst for this reaction, but missed ask question to him, which is better, this one or Nafion? But he's not here. So, anyway, this is an important reaction. And another one is a neopentane cracking. Well, recently, octane cracking, and many papers about cracking have been reported. Now, this one, this condition, this is the highest, and the second, and USI zeolite is a lower activity, And another important reaction is combustion of propane. Now, platinum modified sulfated zirconia and alumina showed 100% conversion at these temperatures. And metal were compared with many kinds of solid acid catalysts, but these two showed the highest catalytic activity for propane combustion. This is also becoming a very important subject in catalysis. Now, another one is acylation reaction. Now, this is this type of reaction. This type of reaction is very difficult to take place. So people use aluminum chloride as a catalyst. But we attempted to use various kind of solid acid for this reaction. Now we found sulfated zirconia showed very high yield for this reaction. Selectivity for para products, sometimes this position and this position. So para position is very important. This acylation is very important because this benzophenone is directly derived to agricultural drug. It's a weed killer. So a very important reaction. And selectivity is 90% in this case. But in the case of aluminum chloride, 95%. That's one disadvantage of this kind of solid supply. Now just you see HGSM5 0, silica alumina 0. So this shows a characteristic feature of this type of solid superacid. Now here another application, or many applications. This one is very well, not important reaction, just a test reaction. Butanol dehydration, cyclopropane isomerization, and you see the effect of sulfate on iron oxide, 2,000 times difference, and this also different at over iron oxide. This reaction doesn't occur even at 200 degrees centigrade. So we see the effect of sulfate on metal, this kind of metal oxides. And here, this is esterification of terephthalic acid with acid. This is also a very important reaction in industry. Now, just compare with silica alumina sulfated titania shows almost more than 90% conversion for this reaction. Basically. And recently, the esterification of other compounds have been reported by some workers. This one also esterification, and sulfated zirconia is the best, and the heteropoly acid is not so high for this reaction. But for different kinds of acylation, esterification reaction, you see this one, titania, sulfated titania, sulfated zirconia, where this, in 2 hours it reacts. So niobic acid is better than solid superacid in this case. So I think it's a very important point. Reactions, esterification reactions where takes place depending on the kinds of acid catalyst and what kind of esterification is very important to choose solid acid catalyst. And this reaction is not so good. But recently, last month, I visited National Chemical Laboratory in Taiwan, and I was surprised to know this type of esterification was very effectively catalyzed by sulfated zirconia. 99 and 80, it's very good catalyst for the this is industrially important esterification of meta-acrylic acid with methanol. Now, in the industry where unvarnished resin are used, but this one, Dow X, it's lower selectivity and lower activity. And now they are doing the test, life test. And now at present 400 hours were no deactivation. If the catalyst life is more than 6 months, this will be commercialized. So very promising application of solid superacid. And another point is alkylation. This compound, now in this case, heteropoly acid, cesium salt, is much higher than sulfated zirconia. So depends on what kind of molecule, reacting molecules. Not only acid strengths, well, just the molecular structure of reacting molecule, well, it's also important. And in my laboratory, many years ago, we reported alkylation of benzene with propylene to get cumene. Well, this is titania zirconia sulfated, titania zirconia show 11, and the HZSN5 and heteropoly acid is lower than this type of solid super acids. And one more example, where this is activity and selectivity of diacetyl methyl silane. Now you can see sulfated zirconia shows the highest activity, but this type tungsten titania the lower activity. And now look at this is C1, C2. So on these solid acids, only C1, C2 hydrocarbon obtained. No silane is formed. This is very also difficult to interpret but in terms of acid streams. So many unknown factors exist for this reaction. And on the other hand, a similar reaction, but E3 reaction, triacylsilane reaction. In this case, tungsten titania is shown the highest, and this is the second or third. But in this case, C2 hydrocarbon almost important where products are obtained over sulfated zirconia and silica aluminum. And tripinin to campaign, this is very important in perfume industry, where in this case, titania, sulfated titania is better than sulfated zirconia or iron oxide. So, more. This is NO reduction with ammonia. This one, well, if one put a small amount, 0.58% of sulfate to molybdenum titania, in that case, sulfate react with titanium to create superacidity. So NO conversion becomes higher. And we examine the relation between acid strength and catalytic activity of this NO removal reaction. So even for this reaction, SO4 effect is very pronounced. And very recently, another papers published about NO reduction with ammonia. Now, usually, vanadium titania is commercially used as catalyst for NO reduction with ammonia. But optimum temperature is like this, 350 or lower than that. But at the higher temperatures, where ammonia is oxidized with vanadium oxide, so this reaction is activity becomes very low. However, only sulfated titania were used, very high selectivity, conversion obtained. This is recently NO removal at a high temperature sometimes becomes important. In that case, well-known vanadium titania cannot be used. In that case, sulfated titania can be used in practical processing. And this one is also this year, 1995, for propane partial oxidation, sulfated one, the red one, is higher than unmodified one. So superacid will enhance the partial oxidation of propane. In this paper, products is not written, so I wrote a letter to the authors, and now recently received his answer. Now, acrylane and acrylic acid, the important material, the selectivity is more than 90%, and not so good for this partial oxidation. However, it is interesting, vanadium zirconia sulfate. So here we see the great effect of sulfate even for oxidation reaction. Now, this is liquefaction of coal. Liquefaction of coal, where without any catalyst, where liquefied products is very low, but iron oxide is a good catalyst for liquefaction, but sulfate will enhance the soluble and fixed and soluble part. Like this. So this is also utilization of soluble superacids. And another one is again Union Chemical Laboratory, Taiwan, where they show this is the ring opening of polymerization tetrahydrofuran, but sulfated zirconia is best, better than hydrochloric acid and zeolite beta. And also it's good. And also this type one, tungsten oxide zirconia, is also good. And they are now testing catalyst life for this reaction. Now, life test is now 2,000 hours. One just become steady. So longer time check is necessary, but very promising for this reaction. This evening they will present posters about this reaction. Now, this is where platinum sulfated sulfate, where hydrogen where is split, heterolytically split into proton and hydride ion. Hydrogen were adsorbed on platinum and dissociate and gave the hydrogen atom. And the hydrogen atom spill over on solid superacids and react with Lewis acid to give protonic acids. So just H2 exposure temperature, higher temperatures, protonic, where acid sites increase. This is due to the dissociation of hydrogen molecule. Now, just briefly talk about the structure of solid superacid. Now, this is characteristic where high frequency absorption. This shows a high double bond nature of sulfur oxygen double bond. We think this is a very important point, which induces by inductive effect where electron shift. Electron shift from zirconium to oxygen sulfur, and then highly acidic site appear. We think it's the most important. Now this morning, Professor Mortera reported, in his case, 1400 Kaiser. Anyway, this is a high frequency. In the case of zirconium or iron sulfate or zirconium sulfate or titanium sulfate, very low frequency, 200 Kaiser lower frequency appears. So this type of complex is very different from usual sulfate. And another important point is by XPS, this highest oxidation state, sulfur 6 plus appear. In that case, it shows superacidity. And with hydrogen sulfide, no superacidity. But if this is oxidized, reoxidized, yeah, this one. But if it oxidized, well, this peak appears. So even any kinds of sulfur compounds will generate superacidity if sulfur oxidation state becomes the highest. Not SO4, any kind, SO2, SO3, H2S, any kind of sulfur compound generates superacidity. And from these results, we concluded the superacid sites is ion of zirconia or titanium. By inductive effect, this site exhibit superacidity. Now, and if basic molecules approaches to solid superacid were based were solved on superacidic sites, in that case, double bond nature decreased. This type of the transformation is repeated by absorption of basic molecules. But this is several years or 10 years ago, we reported. But recently, different well type structures have been proposed by Ransford et al. Well, this is the same with as ours, double bond too. But he says water. This is the water removal will assist the superacidity. And also, you see, it's only one double bond, but this assists the generation of superacidity. And more recently, Professor Knighting in Germany reported by a kind of NMR study this type of structure of solid superacid. In this case, he says double bond is 1, and OH is here. I don't know this is if this is right or not, but that's the publication recently. Now, I want to tell you some preparation, importance of preparation. Corona last year reported where surface area were greatly changed with pH of the precipitating solution. And also tetragonal and monoclinic ratio is also changed. And if you want to superacid on some support, well, some thickness of zirconium oxide is necessary. In this case, no superacidity appears. Only some thickness of zirconia is necessary to generate superacidity. This is useful for application of supported sulfated metal oxide catalyst. And this is so in this case as monolayer. This is not shows superacidity. This type of layer is required for generate superacidity. Now, well, nobody knows this result now because I don't publish it here. Now, this is well, cation pyridine and salt, superacid, or only titanium, and pyridine will donate electron to catalyst to form cation radical. It is measured by ESR spectrum. Now, with sulfate addition, well, oxidizing property of superacid increases. This is a very important point. On the other hand, if you adsorb nitrobenzene on superacid, in that case, well, for reducing side on superacids is decreased. So superacidity generates, and also oxidizing property will generate by addition of sulfate ion. Now I skip, that's almost fine. Now this is commercialized sensor. This is city gas. City gas, for city gas sensor, Matsushita Electric Company developed where iron oxide and some titania, zirconia, tin chloride. Now, if you prepare sensor from nitrate, well, no, very low sensitivity, but sulfate, from sulfate, well, sensitivity increases. In particular, titanium, zircon, tin addition effect is also remarkable. This is application of sulfate, sulfated metal oxide to gas sensor. This is commercialized, but not in the field of catalysis. Now, this is, I'd like to remind you of this one. Sulfate, ammonium sulfate, and ammonium chloride is added to titanium oxide. Isomerization of 1-2 is a test reaction for acidity. Now, this is the one, acidity. So, in this case, 0.5 weight percent of sulfate is added, or ammonium chloride, but it is not much change, but 240 surface area only 2 times. Sulfate addition, effect of sulfate addition is known 1976. So 19 years ago. Nevertheless, at present, no industrial process by using solid superacid. It's pity. It's pity. But probably in near future, I hope. Now, 3 years later, Professor Arata will confirm this. This is fine. Found this is superacid. That is 1979 and 80. Now, factors. Now, this is factors influencing activity of superacidity metal oxide. Now, important metal valency, electronegativity, and coordination number, and saturation. And basicity is also important. And sulfur complex formation, structure is also important. But most important point is the conformity between reactants and superacid. As you saw, many reactions cannot be well explained in terms of acid status. So probably this one, or this one, will participate in activating reactive molecule. So these, elucidation of these facts will be one of the important fundamental research in future. Now, last one is a future trend of solid superacid. Well, I think application to organic synthesis or production of fine chemicals or application to oxidation reaction will be very interesting. And problems for industrial application, deactivation is the most serious deactivation. And the selectivity sometimes low because of very high acid strengths. To solve these problems, where many people use the metal superacid type, where platinum, nickel, and this morning chromium and cobalt, or many modification gives this to solve this problem. And low temperature reaction is very important. If possible, rapid phase reactions will be successful for the reaction by use of solid super acids. Well, it's time, so thank you for the attention.
Thank you, Kozo. I think we have time for a couple of questions.
You proposed a model where you had a sulfate anion coordinating to a single metal. Is there any X-ray evidence for such a configuration?
Well, single metal or the bidentate.
Yeah, bidentate, sure, you have matching configuration, but you had a chelating
Yeah, we wrote, coordinate one metal.
Yeah.
But in that case, always dotted line between acidic and basic sites, where it's hardly determined in the surface.
Right.
So we can, if we can do that, where we can calculate the basic acidic group of reactant molecule, so we can design best catalyst for particular reaction.
Right.
But at present, no. So as you said, intuition is very important based on accumulated data.
Okay, let's thank Professor Tanabe. One of the reasons I'm presiding over the afternoon session is that it saves John Moffat from the awkward position of having to introduce himself. So John's going to be talking about butene isomerization over metal oxygen.
Thanks, Scott.